So welcome back to the channel. Yeah, I know this video is kind of late and we're still solving September 21st question. It's because I'm currently helping the Dog Days event at the University of Washington. So yeah, go Huskies. That's where I'm attending right now. Yeah, and just look at this question right now. So we're given a number n and we want to return all the number in the range 1 inclusive to n inclusive sorted in lexicographical order. So this question also asks you to write an algorithm that runs in of n time and use only linear, use a constant extra space. But I didn't see that constraint before, so I did use like some runtime, like space complexity that's more than of 1. So I will show you two different ways to do it, but first let's dive into what is like a lexical order. So, yep. So let's say I'm given some numbers and then I want you to store it in a lexical order, right? So let's say I give you 2, I give you 10, I give you 100, I give you 1, and I give you 11. And let's say I give you 30. So first thing we want to do is we see the leading one, right? So we know that the 1, this category, 1, 10, 11, and 100 will always come before 2 and 30. So in order to sort this, we'll have 1 first, and then we have 10 as the second. And then since this is like 1, 0, and then instead of coming next to 11, we actually come to 100 first. And then we come to 11. Just compare this, like this is 1 and this is 0. So this will come before this. And then we come to 2 and then we come to 30. So you can basically see if I'm drawing a tree right here, right? So I have 1, 10, 11, 2, 30, and 100. So you can see that I actually going down this path. So whatever comes like as a child of 10 actually come before like the neighbor. So this gives you a sense that you can use a DFS to exhaustively just go through everything in that. So let's try this. Let's look at this. So given like 1 to 13, this is a given example, right? So this is 1, and then you go down 10, 11, 12, 13, and then you have like 2, 3, all the way up to 9. So what will you do here is actually going through this 1 and then add it to the result, and then add 10, and then add 11, add 12, and then add 13, right? So what if I give you like 106, right? So if it's 106, then you still go in 1 first, and then you go in 10, and then you go to 100, and then you go on 101 to 106, and then you go back to 11. So this is like lexical order, is that you go through this and then you do all the DFS. Like you find 100 doesn't have any child, so you roll back here and go to the next one. Until you're done 106, you roll back here, and then like, oh, I have no more child, right? I know more children in 10, then I move to the next neighbor. So this is how it works. And then one case is, it's basically that you need to consider the case where they hit the end and then just go back. So this is basically just DFS. So let's dive into the code and then see if we miss anything here. So let's define a result to be an empty array. And then we know that we need to do a DFS. We do a DFS. And then we want to return the result at the end. All right, so when do we stop a DFS? We stop a DFS if we see like a current number is greater than n, right? So we can pass in the current, and then we said if the current number is greater than n, then we stop. Why is it not greater or equals to? Because when it equals to n is inclusive. So we want to also append n. So by that saying, we want to append the current. if it's in the range, we want to append the current. Then we want to recursively call this. So for I in range, oh my typo. All right, range, what's the range? So we need to think about it, right? And then we need to call DFS. So as we said, when we have this current, we want to go in there, into the child. So how do you go to the child? Go to the child by current times 10, right? If let's say you're 10 right now, so current times 10 is 100. So 100, then you want to go from the range from 0 to 9. So if you want to go from 0 to 9, then it's perfect that you just use in range 10, right? Because it's start from 0 and then this is exclusive. So we can just do this plus I. Alright, then basically you're done. So you're adding all this thing. So only thing you're missing right here is how do you call this DFS function, right? So we want to start with a different current every time. So not like we start with different current, we want to start with the different leading numbers, I'm sorry. So your leading possible number is from 1 to 9, right? So you can say for I in range 1 to 10, because 10 is not inclusive. And then you want to call DFS on the different I. Alright, so this is the first way of doing it. But you can see the memory is actually not very good. Oh, the runtime is also not very good. So the runtime is actually out of n, because you have to go through every n number. And then the space complexity is actually of log base 10n, because all of this is separated by 10. And then we just log 10n for the height of the tree. So this is the space complexity of it. So now let's dive into a second way of doing this. So the second way of doing it is actually an iterative way. So basically, it's the same as a tree right here. Let's see if I can just do this. But instead of building a tree and use a DFS like that, we can just think about the case that you want to return it, right? Let's say for 1, we want to just go in and multiply it by 10, and then we just keep going, right? With multiply by 10, if it's less than n, then we add this. But when we add 100, let's say n is 110, then this is still in the range, then I do it, add 100 into it. When I go down 1,000, 1,000 is out of range, then I don't do it anymore. Then I just print out this plus 1, plus 1, plus 1. When you hit 109, and then you're like, oh, now I'm done, right? I actually not, like, I can't just add 1 to be 110. So if I see a 9 at the ending, I just pop back. So this is one of the cases I pop back. And then just pop back by dividing this by 10. Then you get 10, and then plus 1 here. So you move on to 11. Right? And then when you get to 11, and then you find 1 hen. So if you find that you're actually out of bound again, right? So we need to go to 12. So when you find you're out of bound again, like 110 is out of bound. No, 110 is not about 110, and then you do 111 is out of bound. Then you're like, oh, actually, yeah, we can just pop back again. Pop back by dividing by 10. So this will be 11 and then plus 1. So you move on to 12. And then you find this is not out of bound, but you don't have child, so you just plus 1 and print 13. All the way when you get 19, and then you're like, okay, actually, I think I'm done here with the leading one. So we need just to divide by 10 again. This gives you 1, and then you plus 1 to move on to 2. This is kind of messy, but I hope it's actually makes sense for you. So let's just look at the code if we do it that way. So we can have result equals to empty array still, and then we can set a current equals to 1. And for here, you want to do it until you have enough in your result. So you can either do while the length of the result is less than n, you keep doing it, or you can just say for dash means just a placeholder for in range n means you want to run it n times. I am not sure about like the length of the result less than n, like what's the runtime of checking the length all the time. So this will just keep going without actually checking the length. Yeah, I don't know what's a hidden like runtime behind like checking the length. So we'll just do it this way, and then we can just start by appending the current number into the result. So since you start with 1, right? And then we can check. We need to check if the current times 10 is less than or equals to n only with times 10, right? So basically we want to do current times 10, but what if it go out of bound, right? So we want to check if, if current times 10 is less than or equals to n. If it is, then we make this. Otherwise the case, right? The case is if it's already out of bound, you want that when it is 9, when it's ending at 9, you want to bounce back, right? So if current mode 10 equals to 9, which is the case where here, right, over this 109, you find this is a 9, you just want to bounce back, right? You just want to bounce back. So how do you bounce back is by divide by 10. All right, so if this is the case, you want to bounce back by current divide by 10. And then the other way is when you hit like the max number, which is this case like 110. You don't want to go on to 111 anymore. So you can say, well, current is equals n. You also want to bounce back. And sometimes we confuse about if or a while. So this actually should be a while loop, right? Because if you think about the case where you have 99, 99, 99, 99 or something, or just let's say you have 199. Let's erase this. So let's say you have the case where you have, let's use a blue. This is 19, and then here's 199, right? So now you want to bounce all the way to 2, right? The things come after 199 is actually 2. So you want to divide this by 10, and then you get 19. And then you want to divide 10 again because you don't want to go straight to 20. You want to go back to 2. So this is like a while loop. You want to do it until you didn't see this. So change this to a while loop. And then after all this thing, you add 1 to current. So let's say your current is 199 divided by 10 is 19, divided by 10 again is 1, but 1 is already in the result. So the next value you want to do is actually plus 1 to it. So it's 2. And then at the end, I think this is done. You just need to return result. So this is an iterative way. Oh, it's actually wrong. Oh, so let's see where exactly I make a mistake on. So I just append 10 all the time. So oh, I said current plus 1 equals instead of current plus equals 1. All right, so this is the place. Yeah, so you want to plus 1 into it, and then you just need to return the result. So submit this increase the runtime, and then the memory is better because now we actually just using a constant extra space. We are not using a recursion where you don't have the stack to store whatever you run. All right, I hope this video today is helpful, and I will see you in the next video.